Okay, so this is section 8.3, dealing with the definition of a limit. Before we get into the definition, we want to refresh ourselves on actually the idea of a limit, how we can evaluate it graphically, and how we can evaluate it algebraically. So our first problem is obviously a graphical problem, and it's got some good notation reminders to start us off. It says, use the graph of the function f to find each of the following. Part A says the limit of f of x as x approaches 2 with a little negative up on the right. What does that mean? Approaching from the left. This is a left limit. It's asking what is f of x approaching as x approaches 2 from the left. So you want to think about moving on the x-axis toward x equals 2 from the left. But you want to look at what's happening to our y value. So what is the limit as x approaches 2 from the left? Y value? It is approaching 1, the y value. All right, everybody see that? As I approach from the left, my y value is approaching the value of 1. All right, part B says the limit as x approaches 2 from the right, a little plus up on the right side of the 2 of f of x. So that means we're coming towards 2 from the right. So let's trace our function from the right. What is the y value approaching? Negative 6. There we go. All right. So we talked about a left limit and a right limit. Part C says the limit as x approaches 2. There's no plus or minus there. That is what we call the overall limit. And who remembers the link between the overall limit and the left and right limit? What has to be true about the left limit and the right limit for the overall limit to exist? They have to be the same. And in this case, are they? They are not. So the overall limit then, DNE, does not exist. All right? All right, what about f of 2?
4.
Yeah, that's just the function value at x equals 2, and that is equal to 4. All right, so there's your quick graphical limit review. Now, I picked a couple of algebraic limits that are not basic. They are not just plug in and be happy, okay, because we all know we can do that. So let's remind ourselves, when we do a limit algebraically, the first thing that we try is what? I just said it. Plug in, right? You want to plug in and see what it is approaching. All right. Well, when I plug in, this is the limit as h approaches 0, if you can't see it in the back, sorry, of our function here, 2 times the quantity negative 3 plus h squared minus 18 all over h. Shall I give you a minute to write that down? And stop talking. Once you have it written down, what happens when we plug in? Undefined. Even more important than undefined, we have 0 over 0, don't we? That is your first look at what is called an indeterminate form. Anything over 0 is undefined, but when we have 0 over 0, it takes us that one step further, because there's a contradiction of rules. 0 over anything, we always said, was what? Right, but anything over 0 is undefined. Which rule works? There's a conflict. That's when we end up getting these indeterminate forms. If we get 0 over 0, we need to go down to step 2 here. So what can we do if, when we plug in, we get something strange like 0 over 0? Simplify, yeah. And different ways. What I say is we need to change the look of the problem. And what are the different ways that we can change the look? Stacy?
Well, you can y to the multiply out by negative 3 plus h squared.
Yep.
And then I multiplied that out by 2, so I take the 4 steps with top half, and then I drew it out, or I factored out the h.
Yep.
And then cancel with the h on the bottom.
Very nice. So, first thing we could try is to multiply it out if that's appropriate for the problem. And Daisy talked about the other thing that we can do, which is to factor and cancel. All right. What if there are roots, like this one down here? What's our trick for dealing with roots?
Multiply by the conjugate.
Very nice. Multiply by the conjugate. All right. So those are just three things we can do. There are many more algebraic things we can do to play with problems to change their appearance, but these are three very prevalent, useful tools to making it look different. Okay? So go ahead and do that. So in this one, we're going to multiply it out. We've got some FOILing to do, some distributing, then simplifying and canceling. So try that at your desk. Does everyone have what I have up here? May I erase this so I can work my problem there? Okay? All right. Now, Now, little helpful hints that I'll talk to you about all year long. When we're doing limits, you need to write limits. You should really write it on each step, okay? If you forget to write limit, you will lose a point because you have changed what we are doing. You need to have that limit as h approaches 0 out in front. And when I FOIL this and multiply it out, what do I get? 18. Help me with the rest.
18,
The minus?
minus 12h,
12h
plus 2h squared.
plus 2h squared, and then
Minus 18.
minus 18. All over
H.
H. All right, let's cancel what we can and get rid of what we can. What goes away?
18.
18s are gone. And what can I factor out?
H.
We could do H or 2H. I see a 2H that can come out, leaving me with H minus 6. Is that correct? Okay, all over H. I'm going to write my limit. All right, and what can we do now? We did factor, so now cancel our H. All right, and then we've simplified as far as we can, correct? So now what do I do? Daisy?
You plug the 0 back in for H.
Yeah, I reevaluate my limit by plugging in. So you start that process all over again. Now go back and try and plug in. And I get what? 2 times negative 6 is negative 12. And there is our limit.
Could you not have just pulled it out of the first step?
Pull what out?
And h, so it would be negative 12 plus 2h
Sure.
over 1. Oh,
Yeah,
okay.
that's fine. Yeah. I just saw my common factor is 2H.
Okay.
Either way, it's fine though.
Okay.
But it leads us to something else that is very good in this class. You should celebrate because in Calc BC, on the AP exam, and so that is the way I will grade every test, any form of the correct answer is correct. So, what does that mean? That means if there's a root in the bottom, it's okay. It means if you leave your fraction in a funny form, it happens to be okay. So, Mr. Beamer can't stand this because then I send you to Calc 2-3 where that is not the case. But in this class, it is. And on free response, the main reason the AP, the College Board does this, is it's a matter of time. They are testing your calculus, not whether or not you can reduce a fraction. Okay, so they focus on your calculus skills. So on free response problems, any form of the correct answer is correct. Now, on the AP test and on my test, there will also be multiple choice problems. And multiple choice problems most likely will be simplified. So you do need to be able to do both, but when you're doing a free response, you can save some time by not messing with the little algebraic cleanup at the bottom. Okay? All right. So we are done with this one. So now we have one with roots. Sorry, let's get this out of the way. And here, when we plug in, what happens? Sorry, it is the limit as t approaches 4. I know, I'll try and make them bigger. They look very big on me. All right, the limit is t approaches 4 of t minus root 3t plus 4 over 4 minus t. So,
0 on the bottom.
we get a 0 on the bottom, but let's look at the top as well. 0 on the top? So if it's only 0 on the bottom, like a number over 0, we will draw some other conclusions, okay? But if we get 0 over 0, then we want to change the appearance and things like that. So make sure you look at both, and we'll review about those number over 0 problems later on. All right, 0 over 0, indeterminate. So that means we need to change the look. And on this one, what will I do? Multiply by the conjugate over itself, correct? Because we need to multiply a form of 1. All right, so we've got t minus root 3t plus 4 over 4 minus t times, what is the conjugate?
4 minus 3t.
So the conjugate of the root part, so it's the t plus root 3t plus 4. Little warning, when we do this kind of changing the appearance of the problem, in the denominator, I don't ever multiply them out. If we want things to cancel, we want factors, right? So we don't want to multiply it through and get more terms. So don't worry about distributing or figuring out how to FOIL that bottom. Just the bottom stays the same. 4 minus t plus root 3t plus 4. That's what we have in the denominator. And on the top, what do I have?
T squared.
T squared minus the quantity. I'll let you catch up. So when we FOIL that out, the inner and outer are going to cancel. And we'll just be left with subtracting what?
3t minus 4.
3t, it'll end up
3t
being,
plus
yeah,
4.
thank you, 3t plus 4 in the parentheses, and we'll have to distribute that negative. So now we have the limit as t approaches 4 of t squared minus 3t minus 4 over that large bottom. Okay, what to do? Back to the top. See what we can do. Top factors to what? T minus 4 and t plus 1 over, and let's do our factoring here so we can do our canceling. What can I do to change 4 minus t? Take out a negative 1. All right, so now what? Louder?
Cancel.
We got to cancel on t minus 4. Okay, and so finally, let's try and reevaluate that limit. The limit is t approaches 4 of t plus 1 over negative 1 times t plus root 3t plus 4. What do we get on top? 5 over negative, what do we get on the bottom? 8. So there is our limit, negative 5, 8. All right, well, what would have happened, sorry, cleaning that up a little bit. What would have happened if I still got a 0 over 0? We've changed the look, and it still comes out to be this indeterminate form. Well, what we need to remember, another thing you'll hear often in this class, is there are different ways that we can attack problems. When we go about it algebraically, that's the analytical approach. We also, just as the title of your book says, we also can look at something graphically. So we could graph it and see what the limit is. We can look at something numerically. So we could create a table and have our x values getting closer and closer and closer to 4 from both sides, and then see what our y values are approaching. Okay, so we're not stuck. We just can't go any further algebraically, so we have to look at it a different way. So in here, you'll see the acronym GNAW, G-N-A-W. The last way that we can look at problems or talk about problems is actually in the English written form. Okay, so we'll look at things graphically, numerically, analytically, and in the written form. Right, those are all of our different ways to approach a problem. Okay, so as I said, these limits were not basic ones to start with. We kind of jumped in a little further down the road because we've seen limits before. But when we get back into chapter 2, we'll start back at the basics of limits, okay, and we'll build up again. But I wanted to start out running a little bit here. Any questions on our limits? Okay. So now, we've played with limits. Now let's talk about that definition, that formal definition of a limit, with all kinds of notation, epsilon and delta and the modulus that he talked about. All right, so let's go here. So the way we're going to look at this definition first is graphically, because that's the easiest way to see what's going on. You should write down the definition one time in your notes. This line, this part here, is what we will work with when we do the algebraic approach. So that line becomes very important. Okay, but let's get it into your notes one time. And they asked me last class to make it bigger. So, not there. Oh, I didn't do it. Hold on a sec. Do this. And that. So there you go. Yeah, Michael?
What are those symbols?
Yep, I will talk about them. Okay, so looking at our definition, this is the formal definition of a limit. And I always think of it from here backwards. Okay? So limit as x approaches c of f of x equals 5. That is true if for any given number epsilon, positive number epsilon, such that the absolute value of f of x minus l, well, what is that? Absolute value, what is that on a graph? F of x minus l, absolute value. We're finding a what? A distance. This is the distance between f of x and L. Okay? So if the distance between f of x and L stays less than that epsilon, then there exists some delta such that the distance between our x value and c stays less than that delta. Still a lot to process. Okay, but that's what this is saying. So now let's look at a graph to help us figure out what that means. So this is the limit, L is the limit, if these two things are true. Okay? So let's go look at the graph. All right, so I took the function x cubed plus 4x squared minus 5x minus 3, which is this cubic function, and I zoomed in just around x equals 2. So I'm only looking at this little part right here, and I expanded it over here. All right, when we talk about the limit definition and we talk about this epsilon and this delta, they're usually very, very, very tiny numbers because we're talking about the limit as we get close to some x value, and what is that y value approaching? What is that getting close to? So they are generally tiny numbers. And I want you to think of epsilon on the y. Epsilon is always on the y, and our delta is always on the x. Okay? So the limit as x approaches 2 of f of x equals 11. Is what we are trying to think about right here. So in this case, our C is 2, our L is 11, okay? And I've sketched in epsilon and deltas, but I haven't given them numerical values. All right? So this is true, this limit is true, if for any positive number epsilon, which is the distance between L and this red line up here, and the distance between L and this red line down. For any positive number epsilon, there exists a delta. So to get the delta that corresponds to that epsilon, we take our L plus epsilon to get up here, we come over to our function, and we drop down. Okay? And the delta is the distance from my C to wherever that red is. Okay? So that's a delta. And then I get another delta by subtracting the epsilon, coming over and down, and this is another delta. Okay? They could be the same if we're symmetrical about the point that we're interested in, but they could be different as well. All right, so I have two possible deltas. So the definition says, for any positive epsilon, there exists some delta such that if I get my x value anywhere in this red zone, from left to right, and I go up and over, I stay in the red zone of the epsilon. Okay? So if that's true, then L is our limit. 11 in this case is our limit. If I can find some delta, so that on both sides of this 2, if I stay within that delta distance, I go up and over, and I'm still within the red zone for the epsilon. All right, so basically what we'll be doing is we'll be given some epsilon, and we need to find the delta, either graphically or algebraically. Okay? All right, so let's look at another graph, just to get another look. Oop, not that. And again, if you don't have it all in your notes yet, that's okay. This is going on video. You can look at it tonight, okay? I'd rather you watch me now and understand this kind of confusing concept. All right, so here I took the cube root of x, okay? And here is my c, so the limit as x approaches c is equal to L, and that's what we're trying to show is true using the definition. All right, so I did my L plus epsilon and my L minus epsilon. I go over to my function and come down. So this is one of my deltas. I call it delta 1. When I go down epsilon and come over to the function and come down, then it ends up here. So this distance here I call delta 2. All right? So there should exist some delta such that if I stay within that distance of C, I go up and over, I stay in the red zone for the epsilon. Would both of these deltas work? have to work on both sides of our C? No. Why not? Delta 1's too big. So if I chose a distance right here, and tried to use that as my delta on the left side, it would put me over here. If I go up and over, am I in the red zone? No. So which delta do you choose? The smaller of the two. You're always going to choose the more restrictive delta, because this one, will this work on the right side? Yep, if I come over about there, come up and over, I am still in the red zone. Okay? So I've shown you two graphical examples of this definition when the limit works, right? So let's look at the board real quick and take a look at one where it doesn't work. Okay, so over here we have a function. Tell me about the limit as x approaches 2 of g of x. Just ignoring our definition, knowing what we know about graphical limits. Does the limit as x approaches 2 of g of x equal 3?
No.
No, because?
Because it's not the same from the left and right.
Left and right limits, you'll see me make this in the air, you'll see me do everything in the air all year long. But the left and right limits do not match. Okay, we need them to be like this. So clearly from the graph, that limit does not exist. But let's think about the definition of a limit in analyzing this. All right, so I picked an epsilon of 0.02. Okay, so I want to prove or disprove that the limit as x approaches 2 of g of x is 2. Yes?
Can you take any epsilon from this process?
Yes. But it's only really meaningful if it's close to where we are, yes. Mr. Beamer tells some joke. I don't know even joke. I don't jump in. I'm a good audience. But Astro got his epsilon joke sometimes. Okay, so I chose epsilon to be 0.02, and I just arbitrarily said that's 0.02 on my graph. So if I go up to my limit that I'm trying to figure out if it is right or wrong, go up this much, go over and down, here is my delta 1. And then if I go down the same amount, over and down, here is my delta 2. So which delta would you choose?
2.
You would choose delta 2, the smaller of the two. Does that work on both sides? So when I come over here, delta 2, go up and over, am I in the green zone? No. So clearly, 3 is not the limit as x approaches 2 of g of x. It does not fit in our definition. Okay? So we've looked at it graphically. Now we want to look at it algebraically. And as I said, generally what we're doing is being given an epsilon and finding its corresponding delta. Okay? So we are finding these two values and then picking the smaller of the two. So let's try. Now, your homework for tonight is 1 through 12 in section 8.3. And the 3 problems, I'll probably only get through 2, maybe 2.5. Problems that we're doing in class come directly off that homework. Okay? You can put them in your notes. You do not have to redo them in your homework. It's just taking some of the homework problems off for tonight. Okay? All right. So, let's take a look. Our first one. In exercises 1 and 2, sketch the interval AB on the x-axis with the point C inside. Then find the delta greater than 0 such that the distance between x and C is less than delta. So really, they're giving us this portion right here. And we're going to take the smaller of the two deltas. Okay? So let's go ahead and put our x-axis on there. And we are going to have A, B, and C. A and B are the outer boundaries. C is in the middle. Our C that they're giving us is 1/2. Our B is 4/7. And our A is 4/9. And we want to find the delta that would hold for our definition. So basically, what do we need to do? Compare that do that, and pick
Shorter
a
one.
shorter one. So which one do I choose? 1/14 or 1/8? Small over 2, our delta will equal 1/8. Okay, so they're just doing that bottom analysis there.
So you choose the one that's just closest.
Yeah, the one that would work on both sides.
Got it.
All right, other questions on this? Put the phones away, please. All right. Can I move forward? Kaylee, phone away, please. All right. Now, on this one, here's where we're going to go through and find our delta given some numbers, given a function, and given epsilon. So it says, this should say given a function f of x, and numbers L, C, and epsilon. Find an open interval about C on which the inequality, absolute value of f of x minus L is less than epsilon holds, and then use that to find the delta that makes our second part of the definition hold. So we start with this, and then we use our answer in that to find our delta. So we begin here, and then once we have an answer there, we move to this. Okay? So let's write out, I always start by writing that portion of the definition that we're going to be using. And we're going to start with the right side here to find some values for x that we can use to help us find the delta in the left side of this. So our f of x is what?
2.
2x minus 2. What is my L? Minus 6, so this will be plus 6. Is less than, what's my epsilon? 0.02. All right, and this we're going to solve for x. So we have our input into the other part of the definition. So this becomes absolute value of 2x plus 4 is less than 0.02. How do we solve an absolute value inequality? Well, if we have an absolute value of anything and it's less than 2, I'm sorry, 0.02. Oh dear. Lines are not a good thing for me on here. That means to be less than 0.02 for the distance, because the absolute value is the distance, to be less than 0.02, it's going to be less than 0.02 or what? Greater than
0.02.
negative 0.02. So it's going to fall somewhere in there. Yes? So we take what's inside the absolute value, 2x plus 4, and set up our compound inequality. Less than 0.02 and greater than negative 0.02. Questions on what I have there? Yes, Pat.
How do you get the, like, how would you get it to be negative point, like, 0.1? Because it's an absolute value.
Yes, so if what's in the absolute value comes out to be negative 0.01, you take the absolute value and that is less than 0.02. That's what we're saying. So whatever this comes out to be in here has to be, once we take the absolute value of it, it has to be less than 0.02. Okay, so whatever is in here, that means has to come out to be less than 0.02 or greater than negative 0.02. When I take the absolute value of that, it's still going to be less than 0.02. Yes? So it can be anything. We haven't solved for x yet, but whatever is in here can fall anywhere between those two. So now we'll solve for x, the x that makes that happen. All right, so we can do this all as a compound inequality. Subtract 4 from each side. And we'll get negative 4.02 is less than 2x is less than negative 3.98. And then to solve, finish, what do we do? Divide by 2 everywhere. And we get negative 2.01 is less than x is less than, what, negative 1.99? All right, so those are the boundaries for our x that we can use now to help us calculate our delta. And if you recall, we have a delta on the right and a delta on the left, so that's why we're going to do two different calculations to find our delta and then make our decision. So now we're going to come down from here, and we're going to take that absolute value of x minus c. Well, my x is going to be one of these two. So let me write this. X minus c has to be less than delta. And I'll choose negative 2.01 to calculate first. What is my c value? As x approaches what are we doing in this problem? Negative 2. So it's negative 2.01 plus 2. Absolute value is less than delta. And so we get negative, the absolute value of negative 0.01 is less than delta. So 0.01 is less than delta. And then we'll do the other one, the other side, negative 1.99 plus 2. And do our same calculation. And we get 0.01 is less than delta. So on both of these, we end up with delta is greater than 0.01. Okay? So what that allows us to do is to choose our delta to be this value, because on the left and the right, we came out with the same value. So the delta that we would choose to work in our definition is 0.01. All right, and again, on some of these, when it's not symmetrical, we'd have something like 0.05 and 0.01, and you would choose this smaller. Yes.
Why does it have to be greater than 0.01?
That's the maximum delta that we can use,
Oh.
right? So in our definition, delta would have to be less than that amount on both sides. Okay? Questions? Other questions on this? Okay. Let's start the last one, and I will have it finished in the video tonight, so you can look at it as well. But let's get it started now. Everyone knows homework is 1 through 12, and we have 3 of them already done. Okay. All right. So this is number 9. Again, we're starting the same type of problem, but they asked us to find the limit first. Listen up, please. So part A, we have to find the limit. The limit as x approaches negative 5 of x squared plus 6x plus 5 over x plus 5. So what do we need to do that limit? (25 minus 30 plus 5), we get 0 over 0 again. Change the look. I heard it. Top factors to what? X plus 5 and x plus 1. We get a cancel. And we need to keep writing limits. Please don't leave that off. You will lose points if you do. All right. Now, the other thing that's useful, so when we do this, we'll now plug in our negative 5, and our limit will approach what? what is it? Negative 4. And so our L is negative 4. It's very useful in a lot of these problems to actually have a sketch of the function. So even though it looks a little ugly to begin with, we know that it looks like x plus 1, but with what's going on at x equals negative 5, a whole. So it don't look like that, but at negative 5, and I'm just being arbitrary about where these fall, I've got a whole. Okay? So, as we work with the limit definition, sorry, I'm just trying to extend my line, we can verify the limit that we just did algebraically by looking at the graph, correct? From the left and the right, it's still approaching the same value, the y value, and that y value is negative 4. Okay, so we found our limit. Now we want to do exactly what we did in the last problem, which is to work with this portion first to get our boundaries for x, and then to plug them in here to evaluate our delta. All right, so absolute value of, now, I'll write it out. We have x squared plus 6x plus 5 over x plus 5, and then minus what? Minus L. What's our L? Negative 4, so we get plus 4. All right.